proceed with the third problem. An army contingent of 616 members is to march behind an army band of 32 members in a parade. The two groups are to march in the same group of columns. What is the maximum number of columns in which they can march? This is nothing other than the HCF. We have to find the HCF of 616 and 32. So, as we do, which number is greater? 616 divided by 32. How many times this goes? Let us consider the first two numbers. It goes one time, 32. Remainder is 29. Bring this 6 down. So, this goes how many times? This goes 9 times. 288. Subtract this. What is your remainder? Your remainder is 8. Now, we have to, using Euclid's division lemma, we are finding the HCF. Until we get the remainder 0, we have to proceed this. So, as Euclid, 616 is equal to 32 times 19 plus 8. This is our R. This R should become 0 to get the HCF. Now let's consider these two numbers to proceed the steps. 32 divided by 8. How many times this goes? 4 times. Exactly, it goes 4 times. So your remainder is 0. So now 32 can be written as 32 is equal to 8 times 4 plus 0. So what is your HCF? This is our HCF. HCF for 616 and 32 is 8. So the answer is 8. Let us proceed with the next problem. Division lemma to show that the square of any positive integer is either of the form 3m or 3m plus 1 for some integer m. Let us consider a to be a positive integer. A be any positive integer which is of the form 3q plus 1, 3q plus 2. So, we have 3 cases. When A is a positive integer, we have 3 cases. Let us consider the first case. First case as A is equal to 3q. As in the given problem, square of any positive integer. So, we have to square this positive integer. When we square the left hand side, we have to square the right hand side. So, A square is equal to 3q the whole square. 3q square can be written as 3 into 3q square. Now, this can be rewritten as 3m where m is equal to 3q square. Now, let us consider the next case 3q plus 1. Case 2. The positive integer A is of the form. The next case 3q plus 1 as given square. So, let us square on both sides. So, A square is equal to 3q the whole square. This is of the form A plus B. A square is equal to 3q plus 1 the whole square. This is of the form A plus B the whole square. That is A square. A square is 3q square plus 2ab, 2 into 3q into 1 plus B square. 3q square is 9q square plus 6q plus 1. The first two are multiples of 3. So let us take 3 outside. If you take 3 outside, you will be getting 3q plus 2. 3q square plus 2q. Since 1 is not a multiple of 3, let 1 be written as it is. Now let us rewrite this as m. So you will be having 3m plus 1. Now let us consider the third case. Third case is of the form 3q plus 2. A is equal to 3q plus 2. Let us square on both sides. A square is equal to 3q plus 2 the whole square. 3q plus 2 the whole square. This is of the form A plus B the whole square. So, A square plus 2 into A into B plus B square. a square, 3a square is 3q the whole square, so 9q square plus 2 into 3q into 2 is 12q plus b square, we had 2 square, that is 4. Now let us rewrite this 4 as 3 plus 1. So 9q square plus 12q plus 3 plus 1. These three are multiples of 3. So let us have 3 as a common factor. 3q plus 4, 3q square plus 4q plus 1. This is not a multiple of 3, so let us have as it is. Now this can be rewritten as 3 into m plus 1. So for the first case, when a is equal to 3q, we had a square as 3m. Similarly, when a is equal to 3q plus 1, we had a square as 3m plus 1. The third case, a is equal to 3q plus 2, we had a square as the same 3m plus 1. So, whatever may be the form, 3q, 3q plus 1, 3q plus 2, we are having either of the form 3m or 3m plus 1 while squaring a positive integer. Hence, we have come to the conclusion of the fourth problem. Okay, let us proceed the next problem in the next video.